So now what we're going to look at is we looked at matter, we looked at classifying, and we looked at, how to separate that. But we need to know kind of why things mix and why things don't mix too. So dissolving. So if I put salt in water, we know it dissolves in the water. But what does that really mean? And if we put oil in water, why does that not mix with water? So it all goes to like dissolves like. Okay? So I'm going to put that down, but I'm going to make it a little bit easier, meaning I'm going to use some words, okay, that we haven't talked about. But the word polar mixes with other polar molecules, and nonpolar mixes with nonpolar. So those two things means exactly what that is, okay? So we're going to make this really simple for now, but nonpolar means basically there are no so we know that elements are made of electrons, or have electrons in them. And electrons being moved to one side or the other causes charge. So one side could have more electrons than the other side of an element, and that might cause a charge. So there is no charge on nonpolar, and here we have a charge. And we'll talk about that in a minute, but basically that's the difference. So like dissolves like, polar will mix with other polar molecules, nonpolar will mix with other nonpolar molecules. So let's look at salt and water and why they mix and why oil and water does not, okay? So we need to look at two examples, right? Salt in water, and we're going to go over here like that. And we're going to look at that compared to oil in water. We'll look at the difference between these two, okay? So salt water, basically we need to know what salt looks like. Salt, if you looked at the other videos, we've all done that, and water is H2O, right? And oil, well, I'll put water first. Water is that. Now oil is a long chain of carbons and hydrogens, very long. Okay, so to simplify, I'm just going to put C2H6, okay? And we'll look at what that, I'll actually draw that for you too, so you can kind of see that. But it's actually a lot longer than that, but I'm going to simplify it just to make it so you get the idea, okay? But basically, why does H2O and NaCl mix, and C2H6 and H2O do not mix? And it's all about charging or no charges, okay? So let's look at salt again. I'm going to put that NaCl, all right? And I'm going to put water, H2O. All right. So NaCl has a bond called ionic. We'll get into that later. I'm not worried about you naming bonds right now, but I like to throw things in for future reference. Basically, Na is a metal, sodium. It likes to lose electrons. That's how it will become happy. We'll talk about that again later on. But sodium wants to give its electrons. Chlorine wants electrons, so it's a perfect couple, basically. One wants to give and one wants to take. So I'm going to literally put where the electrons on the other side, so electrons, I'll put a little note here, I'll put it right here. Electrons, E with a little minus, is negatively charged, okay? So electrons, and I guess I'll write it out so that you can remember, electrons are negatively charged. So that means chlorine wants electrons, so it's going to have a negative over here. And because the electrons are on one side, the other side is going to be the opposite. So it's going to be positive over here. So you have a charge. You have a positive side and a negative side. Going into it, why we have charges and all that, that's for future reference. But basically, I just want you to know that salt must have a charge because it can mix with water, which also has it. So why does water have a charge? Well, it's the same idea, okay? So we have oxygen bonded over here, and I'm going to draw how it actually looks. Because there's a bond here with Na and Cl. There's a bond between an H here and a bond between oxygen and H here. So there's two bonds with oxygen, both hydrogens. Oxygen likes electrons. So I'm going to put a negative there. Hydrogen does not want its electrons. Like here, you can have them. So basically the electrons go towards oxygen, And oxygen will have a more negative side because electrons are over there, because remember, electrons are negatively charged. So you're going to have a charge there. So the whole idea is positive and the negative are they're going to attract each other. Opposites attract, right? So I'm going to draw NaCl over here. Remember, it's bonded together, and there's more electrons pulled to chlorine than there are for sodium. So there's going to be a little bit. I'm just going to put a squiggly line, and that's going to be an attraction, not a bond. Because if it was a bond, you couldn't separate salt water by boiling it, because boiling water does not break bonds. It's not strong enough, not hot enough, not enough energy. If you look at separating mixtures and separating pure substances, there's a difference. Check out the other video on that. But basically, this is going to attract each other, and that's how you dissolve. That attraction involves dissolving. So like dissolves like. And you could put another one. You could see that maybe Na over here, another NaCl. It's a positive and a negative, right? So there you go again. Another salt will attract to the water end, the oxygen end. Okay? And of course I can do another one. I could go Cl over here, bonded to the Na. I could do it backwards just so you can see that it doesn't really matter. It's just there's another attraction, okay? Because you got positive over here and negative over there. So they attract each other, okay? So salt and water are dissolving because like dissolves like, and they're both polar molecules. They're both polar, meaning they have a charge. Now, we know water has a charge, okay? But why doesn't oil mix with water? Well, obviously it doesn't have a charge, right? So I'm going to draw out C2H6. So just so you know, I'm going to actually, I guess I could do a lot more. So I'm going to put an X and a Y, meaning it could be a lot of carbons bonded together with a lot of hydrogens. And there's a bunch of different combinations of that. You'll learn that in organic chemistry if you take that in college. But basically, it's just carbon chain, literally. So that's what it looks like, okay, oil. And then all it has is a bunch of hydrogens bonded to it, okay? Now, you can tell, as I'm drawing this, that there's a mirror image of each other, meaning there's no one side that's different than another. So there's a difference between the Na and Cl. I draw that in half. One side is different than the other. So electrons are going to be pulled to one way or the other, making it negative, because electrons are negative. And same here, oxygen and hydrogen are different. Okay? But here, there's no difference. All of the electrons are being pulled in equal ways. So this is no charge. This is non-polar. So there is no charge. It won't attract to the negative end of the oxygen of the water or the positive end of the hydrogen. So so water has these charges to one side and the other, positive and negative, but there's no attraction because oil is evenly distributed its electrons. It's evenly distributed its electrons, so there's no charge. There's no positive end and negative end. So this means no mixing. So no mixing when non-polar mixes, or I shouldn't say the word mixes, is with polar. Okay? So when a non-polar and a polar come together, there's no mixing because there's one that doesn't have a charge and one that does. So make sure you understand that like dissolves alike, and it's based on polar or non-polar. So if there's a molecule that's polar, like water, and it mixes like sugar, then you have to think, well, sugar must be a little bit polar. You have to think about salt. Salt must be a little bit polar. So when something is mixing with water and it does dissolve, then you know it's polar. If it just sits there, it must not be polar like oil. Okay? So hopefully that'll help you understand how dissolving with matter is related to like dissolving like.